Hello everyone, we are going to begin chapter 6, which is uniform circular motion and gravity. In this video, we are primarily going to be talking about centripetal force. And before we get into centripetal force, we need to do a little review. If you recall, Newton's first law says if the vector sum of the forces on an object equals 0, it's going to move at a constant velocity. So if I've got something moving at a constant speed in a straight line or not moving, then I know the sum of the forces on that object equals 0. Newton's second law says that if the sum of the forces acting on an object does not equal 0, it's going to be accelerating. And we've talked in the past about the fact that there are three ways to accelerate: speed up, slow down, and change direction. Well, I have been setting you up for this chapter for the last little bit because now we're ready to start talking about changing direction. Every time an object is going to be moving in an arc or a circle, the sum of the forces acting on it do not equal 0. And we're going to be in a Newton's second law situation. Now, circular motion is any time you've got either a full circle like the orbit of the moon around the Earth or just going on a curve. And whatever fraction of a circle or a whole circle you've got going on, there will always be a net or an unbalanced force making the object move in that circle. The name of that unbalanced force is called the centripetal force. Once in a while I'll overpronounce it and say centripetal force, but the centripetal force is always directed towards the center of a circle. So if I've got an object that's spinning in a circle like this, centripetal force will always be directed towards the center of that circle. And if it's a partial circle or an arc, then it's going to be directed towards that partial circle. This is a force, and so we're typically going to measure it in newtons. Once in a rare while, we'll measure it in pounds. Interesting thing about a centripetal force, if I have an object that is spinning, let's say that this is a ball on the end of a string, and I've got this ball spinning in a circle like this, and at one moment I cut the string and let it go. Now, as long as it is going in a circle, there is going to be a centripetal force acting towards the center. But if I let it go or I cut the string, what's going to be the path of the little ball? So let's make this multiple choice. Let's call this A, B, C, or D. If I am twirling it in a circle, cut the string, which path will the ball take after I cut the string? Well, it's going to be path B, and I apologize I did not draw that as beautifully as I could. And why will it go off as a straight line tangent to the circle? Because of the fact that the ball has inertia. Now, the speed with which the object is going to head off at a tangent to the circle is called instantaneous tangential velocity. And it is just a plain old velocity, meters per second, and we'll deal with that when we start getting to the math. Now, the centripetal force is the name given to a force that's towards the center of a circle. But centripetal force is actually caused by some other force, such as gravity, tension, normal force, friction, and forces we haven't gotten to yet, like electricity and magnetism. So let's go through a small example. Let's say I've got a car, and this car is traveling all around a curved path. There is going to be a force towards the center of the curve, which is my centripetal force. But centripetal force is just the generic name. I want to know specifically what force holds my car on the road. Well, what's it going to be? Friction. Yeah, there is friction between the tires and the road, and in this case, the centripetal force is the friction force. Now, I really happen to know that because I live in Wisconsin, and in Wisconsin, we get icy roads in the wintertime. Now, when this vehicle, if there was no friction and this curve was covered in ice, what would happen? The car is going to go in a straight line because it has inertia. And that straight line is going to be at a tangent to that curve. It's going to go off on its straight line velocity, and off it goes into the ditch. Now, sometimes people say, the inertia is pushing it in that direction. Please, 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 please know that inertia is not a force. Inertia is just a description of the fact that matter likes to keep doing what it's already doing. And we have to have an external force to make it go into a circle. Its natural position, though, is going in a straight line. The centripetal force, as I mentioned, is a generic name. And we have to, before we can do any of the math problems, we have to be able to identify which force is the centripetal force. And here's an analogy. Every woman who has a child is a mother or a mom. Now, but that is not the name that's on her driver's license. On her driver's license, there's going to be another name, Susie or Pang or Esmeralda or something. That's her specific name, and that's what we have to figure out. Centripetal force is kind of the generic name of any force towards the center of the circle, but we've got to know exactly which force we're talking about. So we're going to spend a few slides here trying to identify what is the centripetal force. And let's start with this one, with the gentleman in the hammer throw. Now this object is spinning around him. What force is towards the center of the circle? What is the centripetal force? Well, in this case, it happens to be tension. Tension is how we transfer a force through a rope, a chain, or a cable. So in this case, centripetal force is tension. What about this? This is a little carousel ride. Let's say you've got a small child that's sitting on the carousel. What force is keeping the kid going in a circle? Well, it's got to be a force directed towards the center of the circle. So in this case, what's holding the child on the carousel? Well, probably friction. There's a little bit of friction between the small child and the little horsey. And sometimes there's tension. Many of these rides have a little loop that they put over the child so that they don't fall off. But that's what's providing the centripetal force. Now the Earth is in orbit around the sun. As it orbits the sun, what's producing the centripetal force? Well, sure, that's force of gravity. And force of gravity is also the centripetal force that holds the moon in orbit around the Earth. Okay, this one gets a little tricky. Top view of a washing machine. And when you're done with the spin cycle, all your little socks and t-shirts end up kind of wadded up on the inside of the washing machine drum. My question is, what force is acting on your clothes, keeping them moving in a circle? This force has got to be directed towards the center of the circle. Well, it's not the agitator. So what is it? Well, it's the walls of the drum. The actual walls of the drum are providing a force perpendicular to that surface. So the centripetal force is the normal force. Okay, little washing machine drums all have holes in them. What's the purpose of the holes? Yeah, to let the water out. All right, but here's my question. What makes the water leave the holes? Inertia. Inertia is that tendency of an object to keep doing what it's already doing. And so as the drum spins, the water is going to zip out through those little holes at their tangential velocity, and that is how they separate the clothes from the water. This is a graviton. A graviton is a kind of fair ride some of you may have ridden. It starts out looking something like this. People walk in and they go into the sides and they all kind of stand in their own little cat cubby. Now they spin it very, very, very fast. And after it's spun very, very quickly, they actually drop the floor. So people are kind of suspended on the wall. It's kind of a cool ride. I enjoy it. My question is, what's the centripetal force? What makes the people spin in a circle? And it must be towards the middle of the circle. Normal force. It's just like a washing machine, except the walls are pushing on the people instead of pushing on your wet clothes. Okay, what keeps the people up on the wall instead of sliding down the wall? Well, those of you who have ever been in this ride, you know that the actual back that you lean against is kind of rough. It is sometimes kind of like a carpet or something that has a high coefficient of friction. So it is friction force that is holding them up compared to the force of gravity. This is a fun one. I don't know if you've ever done this. I remember being a small child and watching my uncle do this, and he had a bucket full of water, and the bucket, if he spun it fast enough, he could spin it all the way over his head and not spill a drop of water. I thought he was magic as a small child. My question is, what is providing the centripetal force to keep this in a circle? Well, it's kind of a combination of things. One, there's tension. There's tension in the muscles. The tension is then being transferred into the bucket, and it is the normal force of the bucket at the very, very top that's pushing on the water, making it go in a circle. And also at the tippy, tippy top, one of the forces downward on this water is gravity. Well, if all these forces are directed down, why doesn't the water come out of the bucket? It all has to do with inertia. If you spin fast enough, the bucket is moving so quickly, and remember, it takes time for things to accelerate. If you can move the bucket to a new location at a high enough rate of speed, before the water has a chance to fall that far, you've moved the bucket to catch it. Kind of cool, isn't it? If you're ever on a roller coaster ride, you're exactly the same thing. You're the water in the bucket. What's acting downward? The normal force of the seat and the track. Excuse me. And at the very tippy top, gravity. So you've got to go fast enough at the top so that the car catches you before you fall. One of the things that has been discussed for over 50 years is the fact that if human beings are ever going to go on long distance space travel, we're going to have to come up with some sort of simulated gravity. The human body doesn't function well without a force of gravity. So a spinning portion of spaceships has been hypothesized for years. And the idea is that the astronauts would live and work in these outside spinning zone. And in this case, the normal force caused by the floor spinning would give a simulated force of gravity. And human beings would be healthier in their space travel. Here's another thing that a lot of people would describe as a centripetal force, but it's not really a centripetal force. Have you ever taken a turn really, really quickly and you slide or move in one direction or the other? Well, weird thing. What's going on here is, let's say the black dot is the driver and the orange dot is the passenger. If the driver is wearing his or her seatbelts and the passenger is not, what happens is the passenger, because he or she has inertia, is going to go forward in a straight line, and the car is going to actually move underneath them. Cool, huh? One more idea before we leave and actually start doing some math, and that is the concept of centrifugal force. Now, centrifugal force is the force directed outward from the center of the circle. This word is so much more common in the English language. It's very difficult to watch a sport broadcast without centrifugal force being brought up. But it is the force outward from the center of the circle. Centripetal, the force we've been talking about all this time, is towards the center of a circle. So what is the centrifugal force? In this case, with a hammer throw, it would be a force as the ball goes around. It would be a force outward. As in the bucket example, it would be a force pulling outward. People in the graviton, it would be a force pulling outward. And honestly, there are no magic physics genies out here pulling on this ball as it goes round and round and round and round. There is no such thing as centrifugal or centrifugal force. It's called a fictitious force. But why does this word persist? It persists because of the fact that we feel inertia. As we move these things, we feel the inertia. We feel that tendency of our bodies or the object to want to keep moving in a straight line. And we have to have in our language words to describe what we feel. And so we made up this word, but please understand it is not a force. We're never going to do math with centrifugal force because it's not really a force. All right, that will do for this time. Have a good one. See you later.